Okay, so we're in our penultimate section here, section 9.6. In 9.5, we introduced R combinations, R permutations, or 9.4 and 9.5, one of those two things. So here we're talking about R combinations with repetitions. So we looked at, either in the last section or the one before, we looked at the problem with combinations and repetitions and how that changes how we count things. So we really only have one objective in this section, and that's to look at R combination problems. And our goal here is to showcase how we use R combinations with repetitions and how it changes some of the infrastructure that we've set up in the last couple sections. It's not too different, but there are some important and key changes that we have to make. So the first thing that we set up in true mathematical fashion is a new definition. And we do that so that there's no confusion of what we're talking about. So, R combinations with repetition, we call this a multiset. So this is a multiset of size R. And I wanted a semicolon, not a period. And this is chosen from a set X of n elements it is unsorted I guess unsorted is wrong. Unordered is the word that we want to use. And it's with repetition allowed. So the big thing here is it's repetition allowed, not necessarily enforced. So the elements have to be unordered, not unsorted, because technically they're sorted. They come from our set X. And just because we allow repetition doesn't mean that we're actually going to see repetition. So that's the really important phrasing here, is that yes, we can repeat elements from set X, but we don't necessarily need to. So let's look at an example where we build some multisets. So we are going to, that pen is dying. So we're going to write a complete list of the multisets of size 3 taken from the set 1, 2, 3, 4. So essentially we're saying, what are all the sets of size 3 regardless of what their elements are? So the whole total amount of combinations we can make of any 3 elements from these sets. So we're doing size 3 and we're taking it from 4 elements. So the first set, we can have 1, 1, 1. We can have 1, 1, 2. We can have 1, 1, 3. We can have 1, 1, 4. Now, you'll notice I'm doing something very specific. When you're told to list out all of your multisets, you want to come up with some sort of system or a pattern for you that allows you to know you've hit everything. Because it's hard to know if you just start randomly picking 3 numbers from this set of 4. whether you hit everything. So I start with, this is all the things that have 1, 1 in the first two positions. You can have a 1 in the third, a 2 in the third, a 3 in the fourth, and the fourth in the third. And then the next one down, I go, okay, this is all the sets that have 1 in the first position only, because I already have 1 and 1 in the second position. So that means I can have 2s. So I can have 1, 2, 2. I can have 1, 2, 3. I can have 1, 2, 4. Then I move on here to the 3s in the second position. 1, 3, 3. 1, 3, 4. And then the last one is 1, 4, 4. So at this point, some of you might be going, well, wait a second. You have all these multisets with 1 at the start, and you have 1, 2, 2, 1, 2, 3, 1, 2, 4. What about 1, 2, 1? And the answer is 1, 2, 1 is the same set as 1, 1, 2. Remember that these are unordered sets. So when you construct a multiset 1, 1, 2, this is the same multiset as 1, 2, 1 or 2, 1, 1. So we are actually not only tracking starting with 1, 1 and then starting with 1, but we're also tracking this combination of elements, 2 1s and a 2. I don't need another multiset with 2 1s and a 2 because that's the same multiset. They're unordered. It's not like a sequence. We don't have a specific order to the things that matter. So this set is the same set as 1, 2, 1 and as 2, 1, 1. So that's why we skip them here. It's why when we get to 1, 3, 4, the only set left that has a 1 in the first place is the one that has a 4 and a 4. Because 1, 3, 2 is sitting right here. 1, 3, 1 is sitting up here. 1, 4, 2 is sitting here. 1, 4, 1 is sitting here. And 1, 4, 3 is sitting here. So you have to keep track of that and remember it's unordered. So the next set, this is all of the multisets of size 3 that start with a 1. Now we move on to 2. So we start with 2, and anything that has a 2 and at least 1, 1 has already been written. So 2, 1, 1 is here. 2, 2, 1 is here. 2, 1, 3 is here. 2, 3, 1 is here. 2, 1, 4 is here. 2, 4, 1 is here. And so that leaves us with the things that don't have 1s. So the first multiset of size 3 that has no 1s is 2, 2, 2. Much like the first multiset with 1 was 1, 1, 1. And then the next thing we can do, since we can't have 1s, is just change the last number. So 2, 2, 3, 2, 2, 4. And then we start changing the second number. Now we don't want 2, 3, 2 because that's already here. 2, 3, 2. We don't want 2, 4, 2, so that's already here. So what we're really doing is changing both of these to 2, 3, 3. We can change it to 2, 3, 4. And we can have 2, 4, 4. So now all of the multisets that start with a 2, which means that they have a 2, have been selected, have been written. So now we move on to the ones that start with a 3, which means none of our sets now at this point are going to have a 1 or a 2. So it leaves us with limited options, 3, 3, 3, 3, 3, 4, and 3, 4, 4. Every other combination that we could make with a 3 in it has been written in one of these other sets. And then the last one we have is 4, 4, 4. Every other set, every other combination that you could come up with that has at least one 4 is already in one of these other sets. And if we count all these up, there are 20 total. Now, we don't need to guess the number of multisets that we can construct of a particular size from a specific set, a parent set. We have a theorem that does that for us. And so we'll compare our result. We have 20 sets there, and we'll see if that lines up with this theorem. So the theorem says the number of multisets of size R constructed from a set X of size N is R plus N minus 1, choose R. So the other way we think of this is the number of ways R objects can be selected from N categories with repetition. So if we look back at that example that we just did, we had 4 items or 4 objects, and we were making multisets of size 3. So R plus N minus 1, choose R, is going to be 6, choose 3. And we know that that's going to be 6 factorial over 3 factorial times 3 factorial, or 6 times 5 times 4 over 3 factorial, which will cancel that 6, which is 20. So that's how I knew that there was 20 sets. So this is a great tool when you're constructing multisets. Unfortunately, it does not give you the sets, and there's no great theory or property or process to construct multisets. That's just something we have to do, and it can be tedious depending on the size of your multiset and this number of objects you have, number of elements in your parent set. But you always know how many you're aiming for. So in the homework, when you're building these multisets, or on the next test, you'll calculate how many you know you should have, and that will give you a goal. So you know if you need 36 multisets, and you start making them, and then you get to the end, you think you've done it all, you count them up, you say, oh, that's only 33, I'm missing 3 specific ones. This is why I said in this example here, you want to come up with some sort of pattern or process that works for you. So this is the process that works for me. I start with all the 1s, and I make sure I get every combination that has at least one 1 done, and then I move on to 2s, and then 3s, and then 4s, and so on, and you can obviously extend this to sets that have not numbers. But if you don't like this process, you can come up with your own. There's nothing wrong with that. You just have to come up with a system that works for you, that allows you to get everything, and then you can always check your work by knowing exactly how many multisets you should have come up with. So let's try a couple of examples here, and I encourage you to try this. Make these calculations on your own. So this is just using the theorem. So if there are 15 people, and only 5 types of sodas, how many different assortments can be made for the 15 people? So everyone needs a soda. You're a party planner now. Everyone's got to have a soda. You only have 5 types of sodas available to you. You have 15 people. So you want to know how many different ways can I do this? And so this is just a straight application of picking your N and your R. So N is always the number of choices you have. We have only 5 choices. So N is 5 and R is 15. So this is something that when we have multisets, unlike permutations, you can have selections being made from something that's smaller than your number of choices. So we have 15 people and only 5 sodas. So our theorem says that this is 15 plus 5 minus 1, choose 15. And this is 19, choose 15. Now here, this always has to be the case where the top number is bigger than the bottom number. So if you do this out and all of a sudden you have 15 choose 19, well, that's never going to work because you can't split 15 things up among 19 different buckets, so to speak. So make sure once you've done this that this number on top, when you go to calculate this, is larger than this one. So that's going to be 19 factorial over 15 factorial times 19 minus 15 factorial, or 4 factorial. And when all said and done, your cancellation should get you 19 times 17 times 12, or 3,876 different ways. So this is just this is how this theorem works kind of problem. Now let's add an extra wrinkle to this. Let's say there's a restriction. What if Coca-Cola is one type, and there must be at least 6 cans of Coke? How many assortments can we make now? So our number of choices doesn't change because we still have 5 types. We just now know what one of the types is. So that doesn't change the number of types of soda that we have access to. It just tells us a little bit more information about those choices. Now, what it does change is the selections we're going to make, because we know at least 6 cans need to be Coca-Cola. So that leaves us only 9 selections for each of our assortments left. Now, some people might be going, why do we still pick out of the 5? And the answer is the at least. Because we don't care if all 15 are Coke. That's one of the options in this number here that we just calculated. So one of the 3,876 options is all 15 are Coca-Cola. Another one is where 7 are Coca-Cola. Another is when 8 are Coke, 9 are Coke, 10 are Coke, 11 are Coke, 12, and so on. So we don't exclude those because they're still options. They're still multisets. But we do know that we can't pick more than 9 different options if 6 need to be Coca-Cola. Because what would happen is you would arrange these things randomly, And then you would say, okay, I have my 9 selections, and then add in the 6 Cokes at the end to make up for it. Or you would already have the 6 Cokes in your cooler or whatever it is, and then you'd add the 9 afterwards. So then our theorem says that this should be 9 plus 5 minus 1. Choose 9, which is 13 choose 9. Again, this number is bigger. So this is 13 factorial over 9 factorial times 13 minus 9 factorial, or 13 factorial over 9 factorial times 4 factorial. And when you reduce this down, you should get 13 times 11 times 5, or 715 options. So it limits us. So this is a way that we can still limit our choices, but still allowing for repetition. Whereas if you calculated how many ways can you do groups of 15 from 5 objects without repetition, well, that's not possible because you can't have repetition. So as soon as you hit one choice of each, you're done and you only have a group of 5 instead of 15. So this is a nice way to show how the theorem works and how we can adjust it if we have some restrictions. Where we see this in math used more often is in a problem like this. So how many solutions to x1 plus x2 plus x3 plus x4 plus x5 equals 45 are there if each x sub I is greater than or equal to 0, and this would be for 1 less than or equal to I less than or equal to 5. Right, so each of these variable terms is at least 0. So the way that we think about this is each x sub I is a category. And 45 is the number of single selections. Number of single selections. Because we're adding, so you can think of each of these values, whatever they may be, as tally marks. Our total number of tally marks has to get up to 45. But we could put a tally mark here for 1, and then fit the other 44 into these 4 objects. Or we could put no tally marks here and fit the other 45 tally marks into these 4 categories. So in other words, our categories is our types, and we have 5 of them because we have 5 variables. Our selections, we have 45 tally marks to place, 45 selections to make. So you can think of each of these starts at 0. Every tally mark that you would put down is a counting. It's an index, and you go up 1. Once you go up 1, you're taking 1 away from the total. So if I put 1 here, I have 44 left. If I put 6 here, I only have 39 left to place. But we still have to place all 45 of those tally marks or all 45 of those index increases. So that's how we determine this. These become our categories. This becomes our number of selections. And so our theorem then says there are 45 plus 5 minus 1. Choose 45, which is 49 choose 45. 49 factorial over 45 factorial times 49 minus 45 factorial. And so this comes out to be 211,876 different ways. Or in other words, there are this many solutions. Now, a lot of times in math, we say, well, there's an infinite number of ways we could add 2 numbers to get to another number. The key here is we've placed a restriction onto our problem. We have to add positive numbers. And once you place that restriction, that reduces your total options. There's still a ton, almost 250,000 different solutions we could come up with. So every single one of us in the class could come up with 5 different numbers that add up to 45, starting at 0. But this is how we can find how many solutions there are. Now, what happens if we change this ever so slightly, and we say, well, what if x sub I has to be greater than or 1? Right? We still have x1 plus x2 plus x3 plus x5 equals 45. Well, we still have 5 categories. There's still 5 variables to fill up. So you can think of each of these as a little bucket, like I've been saying. We have x1, we have x2, we have x3, we have x4, and we have x5. And now we have 1 tally mark in each of these to start. And all together, this has to get up to 45 total tally marks. So we have 1 in each of our categories to begin with. Well, we still have 5 choices. Only now, how many total tally marks are we going to place? Well, because of this new restriction, 4 of those choices have been taken away from us. It's just like the Coke cans all over again. So we don't have 45 choices to make, we only have 40 choices to make. So this would be 40 plus 5 minus 1, choose 40 factorial, choose 40 factorial, or 44, choose 40 factorial. Why do I keep saying factorial? 44, choose 40. Choose 40 factorial would be enormous. And so when you write this out and simplify, I'm running out of space here, but this is 44 factorial over 40 factorial times 4 factorial. And this comes out to be 135,751 options, if I've done my multiplication correctly. And so if we compare this to the last result, it should be less, and it should be a lot less because we're taking away a lot of options by already placing 1 tally mark for each of these variables, or 1 digit. But this is how we can, this is the mathematical version of that Coke can problem. We look at how many ways we can place any number starting with 0, and then we place restrictions. Now, if we lift these restrictions, and we go to the original problem, and we say, well, our x value for each one can be anything. Well, then there truly are infinite different ways we could do that. Because we can always pick x1 to be negative x2, and then x3, x4, and x5 have all the things. We could pick x1 to be negative x2 plus x3 plus x4 plus x5. We could pick x1 to be negative x2 plus x3 plus x4, and then have x5 be 45. There are too many ways if we don't have this restriction here, or similarly, we don't have this restriction here. So these restrictions are important to limit the number of selections, the number of options we can actually make. But this is how we handle combinations with repetitions or multisets. And with that is the end of 9.6.